In this video, I will introduce Zernike terms as it relates to DFTFringe by Dale Eason, and in particular talk about the Null feature. It's quite possible that this video will only give you a rough understanding, but I hope it helps you on your way to comprehending Zernike terms. I have instructions on how to make a bath interferometer for under $100 or buy one for under $150 at my website at gr5.org/bath. I have other instructional videos on this YouTube channel related to interferometers. Zernike polynomials are named after Frits Zernike, a Dutch physicist. There's a great Wikipedia article that explains the polynomials in more detail. First, note that I will use the term wavefront error instead of surface error. Normally, for mirrors, the wavefront error is double the surface error. For example, if your mirror has a dimple that is 1 wavelength deep, the reflected wavefront will have an error of 2 wavelengths because the light of the testing wavefront goes down to the bottom of the dimple and also back up to the level of the mirror surface. Typically, when testing mirrors, we are dealing with 2 different wavelengths. Typically, a mirror is tested with a red laser around 650 nanometers. But when we talk about mirror accuracy, we want to define the performance using 550 nanometers light, which is a shade of green near the middle of the visible spectrum and also near where the human eye is most sensitive. DFTFringe automatically translates for us between the wavelength of the I-gram, typically 650 nanometers, and the accuracy of the mirror wavefront, typically 550 nanometers. For this video, don't think in surface distance, think in wavefront, but in the back of your mind, just know the surface is half the error of the wavefront. Using Zernike terms, we can break up the surface error of a mirror into separate orthogonal components that represent particular shapes. For example, 2 of them are called X-tilt and Y-tilt by DFTFringe. Other people might call these tip and tilt, or tip and twist, or pitch and yaw. Orthogonality means that each of the terms are independent. They don't affect each other. Zernike terms are a way to split up all the errors or characteristics of a wavefront into separate items so we can look at each one separately. You can then combine the Zernike terms to reconstruct the original wavefront, or close enough. To get it exact, you would need more than just the 47 Zernike terms that DFTFringe uses, but 47 terms gets the mirror tester amazingly close. The concept of orthogonality is very important. It implies you can change one thing, like tilt, without affecting any other term. Your I-gram can have a lot of tilt or defocus, and it won't affect the measured spherical aberration. If you are familiar with Fourier transforms, this is very similar. A Fourier transform can convert a waveform into many orthogonal sine waves in the frequency domain. You can examine or modify these sine waves and then convert back to the original or edited waveform. The same is true with Zernike terms, except that they are for 2-dimensional circular waveforms, which is great for lenses and telescope mirrors as they are circular. Let's talk about tilt for a few minutes. Tilt is the tilt of your wavefront, which is double the tilt of your mirror. I'm going to choose Simulations I-gram. I click the Clear All button to clear all the Wyant terms, and I'm going to set the X-tilt to 2 units. I click OK, and this is what a perfect spherical mirror would look like. Because I entered 2, it's approximately 2 waves closer to us on the right side versus the center, and 2 waves farther from us on the left side versus the center. Note that the pattern is symmetrical, and there's no way for a human or for DFTFringe to know if the right side of the mirror or if the left side is closer. This is the whole purpose of the invert wavefront feature, but we'll talk about that later. Let's give it more tilt. I do it again and change tilt to 10. I click OK. This gives us exactly 20 waves, 10 left of center and 10 right of center. Now we can click Done, adjust center filter, and click Compute Surface. Always click No to this when doing simulations, as once you click Yes, it will silently decide when to invert without asking you until you restart DFTFringe. We see a wavefront with a lot of spherical aberration. That's because I have my null turned on. Let's turn it off. Configuration mirror, uncheck artificial null. Okay, we have a perfectly spherical mirror. Notice the strail is a perfect 1.0, RMS wavefront is 0.002 waves, or 1/500th of a wave of error. RMS is a kind of average. It stands for root mean square. It's a more useful number than a pure average for determining overall error. Notice it has a tilt of 10. We got lucky. It could have chosen -10. Let's enable X-tilt by selecting the checkbox, then click the Recompute button, and we can see the tilt. That's what 10 waves of tilt look like. Zooming in, we can see the vertical scale is 0.125 or 1/8th wave. Zooming out, we see the right side of the mirror is many waves closer, and the left side is many waves farther. By default, the tilt Zernike term is unchecked because having a tilted mirror is not considered an error in the mirror, and in fact without at least 10 waves of tilt, the accuracy of DFTFringe goes down. Dale, the author of DFTFringe, recommends at least 18 fringes, a tilt of 9, and people have found that even more fringes, maybe 40 to 80, tends to increase resolution and accuracy up to a point. You need at least 3 pixels per fringe in your camera though, so at some point you have too much tilt. In general though, 18 fringes is enough for accurate measurements. But the tilt term is far from useless to us. When we took the measurement using the interferometer, if we purposely moved the bath to the right until we saw 20 waves, and made a note of that information, then we know to expect this X-tilt to be positive. If DFTFringe reports it as negative, then we need to invert the wavefront with this button here. If we don't do that, then every error on the surface shown in DFTFringe is upside down. Bumps are holes and holes are bumps. Similarly, if we move the bath upwards, we get positive Y-tilt. If the mirror is tilted in an angle other than horizontal or vertical, then you get a combination of X and Y tilt. For example, let's look at fringes for X tilt of 10 and Y tilt of 3. You can get the angle of tilt and the amount of fringes to any value by changing X and Y tilt. Let's look at spherical aberration. First of all, what is it? When talking about a telescope mirror, you want a parabolic surface to collect starlight from a single star to focus on one point. This leftmost diagram shows parallel light rays coming downward from a distant point source, such as a star. They bounce off the parabolic mirror and come to a single point called the focus. In the second diagram, you have the same thing, but because it is a spherical mirror and not a parabolic mirror, light hitting different parts of the mirror focuses at different focal lengths. This is bad. This error, where different ring zones of the mirror focus to different focal lengths, is called spherical aberration. On a wavefront, spherical aberration looks like this, and this is the 8th Zernike term. However, the bath interferometer, and by the way, Foucault test and Rankine test, works at the center of curvature, or COC. COC is twice as far from the mirror as the focal length, which is why these diagrams are twice as tall. The light rays are not coming from infinitely far away, but instead from the COC, and the light returns to the COC. So focus is at the COC in this example. This third diagram shows the same spherical mirror as the second diagram. The interferogram of a perfect spherical mirror will have no spherical aberration in the interferogram. Now the fourth and final diagram shows a parabolic mirror. As you can see, it has different focus points. Notice how the multiple focus points are very similar to the second diagram where different ring zones of the mirror focus on different focal lengths. This is also called spherical aberration. You might think it's different from the other spherical aberration, but the wavefront has the exact same shape. So when testing with a bath interferometer, the difference between a perfect spherical mirror and a perfect parabolic mirror exists only in the spherical aberration term of the Zernike terms. The amount of spherical aberration depends on the diameter length and focal length of the mirror, and also the wavelength of the light you are using, because Zernike terms are presented in a particular wavelength of light. The Bath interferometer sees no wavefront error for perfectly spherical convex mirrors. So any wavefront shapes are shapes different from a sphere. Since spherical aberration is the only Zernike term that changes in a parabola versus a sphere, then the perfect parabolic mirror should have only spherical aberration when at COC. If the mirror is a little inside or outside of focus or to the side of focus, this will affect tilt and defocus only. We'll talk about defocus soon. It will not affect other Zernike terms. Let's look at my own personal mirror here and go into Configuration Mirror. After entering my mirror diameter and radius of curvature, after I set conic constant to -1 for parabolas, and after I enter my laser wavelength, you can see my artificial null is -0.454241 waves. This means that we want spherical aberration to be -0.454 for my mirror to be a perfect parabola. This time, let's go into Simulation Wavefront. This allows us to skip the I-gram, skip the processing of that I-gram, and go directly to a simulated wavefront. Spherical aberration is so important to our analysis, it has extra features. If we enter 100 here, and if this radio button is set to correction %, then this will automatically fill in my mirror's null value of -0.454241. Instead, I'm going to click the Z8 radio button and put in -0.4 for spherical. Note that Z8 is the 8th Zernike term if you count piston as Z0. So Z8 represents spherical aberration. I click OK, and the program calculates that we get a very good mirror. Here we see Strail is 0.97 out of a possible 1. RMS error is 0.027. That's about a 30th of a wave. Note that best fit conic should be -1 for a perfect parabola, but is instead undercorrected by about 12%. This is because I entered -0.4 for spherical aberration in the simulation instead of entering -0.454. We can see that the 0.054 error in the spherical term here, which is the difference between 0.4 and 0.454, and that is contributing 0.024 waves of the 0.027 RMS error. If we zoom in on this 3D view, we can see how the center and edges are a little high. This mirror is undercorrected by 12%, but it's a pretty good mirror. A mirror maker might say it could use slightly more zonal correction. We can click the Star Test tab and see what a star would look like at focus, inside focus, and outside focus. I wish my real-life mirror was 0.97 Strail. Let's look at astigmatism. I mentioned in my quick start video that astigmatism looks like a Pringle potato chip. In the eyepiece of a telescope with astigmatism, stars tend to look less round and more like a dash, not necessarily horizontal or vertical. Astigmatism is not good. Let's additionally enter 0.3 wave X and Y astigmatism. There you go, Pringle potato chip. Let's uncheck Y astig and look at X only. X astigmatism has the sides of the mirror closer to us. Negative X astig has the top and bottom of the mirror closer to us. Let's look at the Y astig only. So Y astig isn't the best name for this Zernike term. Some people call it order 45, some call it oblique astigmatism. Y astig is what DFTFringe calls this, but 45 astig I think would be a better name. Anyway, if you combine the right amounts of X and Y astig, you can get any rotation of the potato chip and any magnitude. Astigmatism is going to be the most common error you see in interferometry, and it probably won't be from the mirror surface. It can come from the bath itself. The greater the separation of the two beams and the faster the mirror, the more astigmatism you can expect, mostly X astig. Also, air stratification will cause astigmatism. Warmer air is less dense and has a different index of refraction. If the air in your room is still, but is 3 degrees warmer at the ceiling versus the floor, then this acts like a prism that bends or curves the light and will cause astigmatism in the wavefront that isn't part of the mirror. This is usually not 100% in the X-astig because of the shape of temperature gradients in your room, but will be mostly X-astig. By the way, this can be eliminated by using a vertical test chamber, or by testing in a vacuum. Using a simple plywood test tunnel can help a lot also. Your test stand that holds the mirror can also induce astigmatism by bending the mirror slightly. Because of the various causes of astigmatism, we always take at least one additional I-gram with the mirror rotated 90 degrees. We back-rotate the second wavefront in DFTFringe by 90 degrees, and when averaging those two wavefronts, any astigmatism from the air or from the bath should cancel out. If you add 2 Pringle chips of error that are rotated 90 degrees, they cancel out. Any remaining astigmatism would be in your mirror, hopefully, if the error didn't change between measurements. But we are getting beyond the scope of this discussion. Let's talk about that pesky question about inverting the wavefront, which inverts the wavefront topology. It does the same thing as this invert button here, except that the pop-up dialog remembers your answer if you click yes, and checks the sign of the spherical aberration versus your mirror. I'll explain better, but first let's hit this invert button. Select a wavefront, click invert. It inverts all the z-values or heights of your mirror. Now we see a huge amount of spherical aberration, 0.854. This is the sum of the actual spherical aberration subtracted from the null value. I had entered minus 0.4 in the simulation, but now we inverted it to plus 0.4. Subtract minus 0.454 and you get 0.854. Because DFTFringe is used mostly to test parabolic mirrors, if your mirror is even slightly parabolic, then it should have negative spherical aberration. Whenever you get to this Results tab and spherical aberration is the opposite sign as the null value, then DFTFringe guesses, usually correctly, that you need to invert the wavefront. Once you click yes one time though, it will automatically flip any wavefront that has a spherical aberration opposite that of the null. Until you halt and restart DFTFringe, it will never ask again and always do the inversion automatically. If your mirror is close to a sphere, this could be a problem. I plan to have another video on how to know when to invert. It is important to the mirror maker to avoid making a low zone worse because they are looking at an inverted wavefront. Positive defocus means you position the interferometer outside of focus. 0 means you are exactly at focus. This Zernike term is normally unchecked because it doesn't contribute to any errors in the mirror. It's recommended to keep this near 0. I prefer to keep this less than 4 waves. Notice that the X and Y Coma Zernike terms are unchecked. Coma is difficult to measure accurately with a bath interferometer. Coma is always removed in a Newtonian telescope by proper standard collimation procedures involving tilt and decentering. Thus we don't care about the value that may be on the mirror. So that's my brief explanation of Zernike terms. If you play with the simulator and DFTFringe, your understanding will grow. For example, if you forget if positive x-tilt means the left versus right side of the mirror is closer, then you can ask DFTFringe by entering a positive tilt in the simulator. If you want to learn what trefoil is, you can just also use the simulator. If you're planning to test a 1 meter f3 mirror and want to see what an I-gram might look like, again, try the simulator. Over the past year, I have personally done hundreds of simulations to increase my understanding. I sell inexpensive interferometer kits and have instructions on how to make a bath interferometer for under $100 at my website at gr5.org/bath. I have more videos in this YouTube channel.